Let me introduce our first speaker, Ben Pfaff. Ben has been a researcher at VMware since 2020. He's one of the first employees at Nicira when he founded the Open vSwitch project and contributed also to the OpenFlow specification. When VMware acquired Nicira, Ben continued to work on Open vSwitch and went on to found the OVN project as well. He's a senior member of the ACM, a fellow of the Open Networking Foundation, and he's been active in open source developer since 1995. Before Open vSwitch was a contributor to Debian and GNU and other projects of that sort. He received his PhD from Stanford in 2007. Without further ado, Ben, take it away.
Thanks, Larry. Let me share my screen here, and then I'll get started. It looks to me like everything's shared properly, so I'll jump right in. So today I have some observations to share about how distributing policy scales in an SDN system, and let's jump right in to what I have to say about that. So before I really get started, I need to give some of the context for what I'm going to talk about. I'm talking mostly about data center environments where I've spent a lot of time working on network virtualization systems, and in particular, I'm going to tell you a little bit about how I define network virtualization, because that's important to the sorts of things I'm going to talk about. I've worked with OpenFlow a lot more than I've worked with P4. So some of what I'm going to talk about is going to mention OpenFlow. I have started to do more with P4 lately, and there's a 5-minute talk elsewhere in this workshop where I talk about some of that. I've barely worked with hardware switches at all, so the network virtualization systems that I've built and that I tend to think about tend to tunnel around the hardware more than using it directly to implement the application. So let me tell you what I mean by network virtualization. Suppose you have some virtual machines. They could be containers. It doesn't really matter. Anyway, let's call them the green VMs. You can see green VMs A and B and C on your screen here. And you want all of them to be able to talk to each other through a switch. And we have a green switch here. And then suppose you also have some purple VMs. I've labeled them D and E on the bottom, and you want them to be able to talk to each other, but not to the green ones. So you connect them with their own switch. So far, all these could just be servers instead of VMs, and they could be connected by physical switches instead of virtual ones. To make it network virtualization, look at the physical servers running the VMs, these blue servers that we have on the right. These servers have one physical network. They don't have a green network and a purple one. And we arbitrarily stick each of the VMs on one of these physical servers and make it work out properly so that the green VMs can only talk to the other green VMs, and the purple VMs can only talk to the other purple VMs. And in addition, they have separate network namespaces so that they can have overlapping IP addresses, overlapping Ethernet addresses. They're not even aware, and they don't care that the other virtual machines exist. The network virtualization system makes it work regardless of how the VMs move around in the system. So you can implement this a few different ways. If in a very basic way, you could use VLANs or you could use VXLANs. The ways that you might implement this are the context for the rest of my talk. So now here's what I actually want to talk about now that I've gotten through the introduction. For me, it's the number one question in software packet processing. In my experience, it's when a packet shows up, what do we need to do with it? In software, it's often more expensive to figure out what to do with a packet than to actually do it, because usually what you want to do is just send the packet somewhere, and that's pretty straightforward, and the hardware is good at that. But that's not what I'm going to talk about today. I like talking about classifiers, but I'm not going to go into them. Instead, I want to talk about a different aspect of the question of how to decide what to do with a packet. And let me get into that. What I'm going to do is a little bit of big O arithmetic on virtual machines and the policies behind them. And I'd really love to get feedback on whether what I'm saying here makes sense. I haven't heard other people express it quite this way, and maybe there's something important I'm missing. So let's start out by saying that we've got n VMs. They could actually be containers. Like I said, it just doesn't matter for this purpose. So since we've got n VMs, we've also got a big O of n policy data, since we need at least some data for each of the VMs. At the very least, you need the VM's Ethernet and IP address, and the information on what server is hosting that VM and where to find that that server that's hosting it. So these n VMs of ours are in practice packed at least a few to a server node, but at most a constant factor. That means that in addition to O of n VMs, we also have O of n server nodes or hypervisors that are hosting them. So the final key point that I want to make here that that all of this hinges on is that in the most straightforward way that we would build a network virtualization system, we have to take all of this O of n policy data and distribute it to all O of n nodes, which means that we need to transmit O of n times n, O of n squared policy data. So that then the question is, how do we distribute that O of n squared data? It's expensive, and as our system gets big, as n gets big, that's going to be too expensive to scale gracefully. It doesn't matter how we do it. It will always require sending that much data on the network unless we use multicast. I'm not aware of systems that use multicast for this purpose in a network virtualization system. I'd love to hear about it. Maybe maybe there's a system that I just don't know about. So in because of this, in my experience in building network virtualization systems, a big design decision is simply, how do we compromise in some place to make the system scale? And that's what I'm going to talk about for the rest of the talk. That is, what are the ways that we can compromise in some manner to make this scale to a sufficiently large n. None of this is profound, but I haven't seen all of these approaches described together, even in the fairly superficial way that I'm going to do it. So I'm going to go through a number of these ways, and the first one is maybe the most trivial, which is to say that that we ensure that things can scale well by just not scaling them very big. If n is small, then big O of n squared is perfectly practical. And we've seen this in practice. I've seen this in practice a number of times. All of the network virtualization systems I've worked on have had initial versions where we expected that there just wasn't a goal to expand very high. One example is that the OVN system that I founded, we decided in the architecture that our initial goal was to design it so the bottlenecks would be reasonable up to a particular size. We weren't quite sure how big that would be. It turned out that when some third parties tested it, it worked okay up to about 2,000 VMs. Great. And the perhaps surprising thing is that this is actually good enough for a lot of users. In surveys I've seen, most enterprises, and most enterprises aren't the gigantic enterprises, obviously. Most enterprises have 7 or fewer racks of equipment, which means that 2,000 VMs might be perfectly fine. to some extent, the strategy is just a try it and hope it works up to the size that you care about. So we can also do clever things to reduce the constant factors in our calculation. None of these reduce the big O, but all of them help scale your system further before the big O really bites. So for example, if our network has a lot of uniformity, like for example, most of the VMs have similar policies, then maybe we can factor that out with some kind of grouping or inheritance kind of mechanism. A second strategy is that we can assume that most of the time, that most of the nodes, for one reason or another, don't need most of the policies, and so you don't have to send those policies to them. That can be a good assumption, but sometimes you end up with users giving you systems that require the worst case, and then your assumption fails and your system gets slow. There's different kinds of compression you can do that will help. And finally, you can keep your system really simple, which is often the case in the first couple of versions of it, or you can keep your configuration of it really simple. My experience is that people start out simple and they want things that are more complicated or more sophisticated over time, so it doesn't last. So that's two ideas. I have some more. So here's one that might work. I don't know whether anyone has really tried this. So if you remember SDN controllers back in the early days of 2008, 2009, 2010, they didn't distribute all the policy data at the beginning. Instead, they waited for traffic to show up, and then they told the switches what to do 1 microflow at the time. This was really easy to program at the controller, but it had bad network performance and it failed hard if the controller wasn't accessible. And we gave up on the reactive approach as an industry, I think, more or less entirely, and for good reason. But there might be reasons to revisit this kind of design these days. So if you look at Open vSwitch, for example, internally it was once reactive in just the same way. When a packet showed up, it set up a microflow for it inside a single chassis. It had some of the same latency problems and load problems that remote controllers did. But we came up with a twist on it where we set up a flow that was bigger than a microflow when a traffic showed up, which cached better and avoided a lot of these performance problems. Is it possible to do something like that for network virtualization? And would it be effective? I personally think it's worth looking into. It would, at any rate, I've got a catchy name for it already. We could call it gigaflows. Okay, so here's a fourth approach. If we have a big network with a big N, and then we divide it up into a hierarchy of smaller networks with smaller N's, then each of those smaller networks would naturally suffer less from this n² problem. If your network divides up naturally, this seems like a great approach. If it doesn't, on the other hand, you don't win anything because you have to distribute all of the policy to everyone, and you've just invented a more complicated way to do that. Here's a fifth approach, which is to say that if your network doesn't change, if it's static, then maybe it just doesn't matter that there's a lot of policy data because you only distribute it once at the beginning of time or only occasionally when the network does actually change. Here's what you might say is a truly revolutionary idea. Do we really need SDN at all? SDN is all about centralization, but we might not really need it. If the hypervisor nodes in our network can make do without knowing all the policy in the general case, then maybe we've got something where a general purpose network virtualization system is overkill. Maybe we don't need it. Maybe we can just use something simple that uses less communication. Okay, we're almost to the end of my list. This is my second to last suggestion for where to compromise in this kind of a system so that we can distribute less data. And that is that we might be able to make our VMs and containers so uniform that we don't need to transmit anything about them at all. I've read some papers, for example, where the hierarchy and policy of our physical and logical networks get encoded right into Ethernet and IP or IPv6 addresses. And if you do that, that means that the hypervisors can figure out what to do with a particular packet, whether they're sending or receiving it, without having to look up anything in one big table. Instead, they just do a simpler computation or look up in a tiny table. I think that these are specialty cases, but they're great if you've got one. So here's my final approach that I'm going to talk about that can also help. This is one where I spent a lot of time in the OVN network virtualization system. So I'll go into a little more detail than the others. Consider the OVN network virtualization system. OVN uses OpenFlow and other bits that you won't find in other systems, but I think there are parts of it that are representative in the other ones. So in a typical system, you'll find that the NVMs end up producing O of n table entries, which OVN represents as what it calls logical flows. And you can see sort of a data data flow chart here, and you can see that that's what happens in these from A to C there. And then in D, we replicate and we send all of that data to all of the nodes in the system, and then in E and F and G, those nodes take that data and compute on it locally and set things up so that they can implement the policy of the system on their local nodes. So in a typical system, what you've got is you're distributing, you're doing computation on the full data, you're sending the full data, and then you're computing on the full data. But we can also build a system so that it's incremental, so that after your system starts up, each small change trickles down through a proportional amount of computation, which only produces O of n bandwidth on a change, on a small change, and only O of 1 computation on each node for a small change. This does take some new assumptions. So let me mention what those are, because we can't really do this sort of thing unless these assumptions are true. And I've got a list of all of the assumptions that we have to make at each of the stages here to actually believe that that this is going to work. And the key ones are, first of all, that in B and in F here, you have to be able to, when there's a small change to our configuration, or that there's a small change to the per node state, that you can compute what the output of those computations should be efficiently. And I'll talk about that a little bit more in a minute. And then in C, we have to believe that the size of a change to how the system should behave is proportional to the size of the change in the configuration. So I'll talk about that also just a little bit. So let's see. I'm running a little low on time, so I'm actually going to skip over this part here because I want to talk about the other part a little bit more. So I mentioned that we have to be able to compute our system state efficiently based on an incremental change to the input. And this is actually quite hard. If you try to write a program in a traditional language like C or Java, then writing a general program to do incremental computations is hard. And so you have to come up with some plausible means for doing that. And we've tried 3 different approaches in OVN over time. First, we did an ad hoc approach in C. And what we found was that it was too hard to make this reliable, which I've always said was true, but we kind of proved that. Uh, Number 2, we tried a more disciplined approach where we used an engine of callbacks, etc. This approach appears to work. It's quite difficult to write, and it's quite difficult to prove that it's correct in general, and it's difficult to make as general as you might want. And it has a few known issues, but it does seem to work. The primary approach, though, I want to push is to use a language that automatically implements incremental computations. And we used one called DDlog. And I think that this approach shows a lot of promise. There's another talk in this workshop about a project called NERPA that uses DDlog. And if you're interested in this approach, you might want to follow up by watching that talk as well. And I don't have time to go over the statistics here, but in the best case, this makes a huge difference. You can come up with worst cases where it's really bad. So in general, I'd say more research needed. And I want to thank everyone for listening. I meant this talk to be thought-provoking, and I'd like to hear your thoughts on whether the problem that I'm talking about here makes sense and whether there's a better or more general solution than what I've thought of. Let me know what you think, and I'm ready for questions.
Hey, thanks, Ben. That was thought-provoking. We have one question typed in so far, which I'll start with, but then I have a bunch of other ones I want to follow up on. But it's kind of interesting. The question is, why not limit the network to a tree or a DAG? And I know you talked about multicast assumptions at the first, but this kind of teases out this gray area between centralized control versus distributed control. I mean, the limit, why not let the nodes just figure it out for themselves? Could you speak to that a little bit?
So we have at least 2 kinds of networks here. We have the physical network that spans the nodes that actually gets packets to and from our VMs. And then we have our logical networks where we specify the connectivity between the VMs. I'm not quite sure. So usually the goal is to let the user, the administrator, connect those VMs however they like in the logical network, and then map it to whatever physical network we're kind of stuck with from the system's point of view. I'm not quite sure which network we'd want to limit to that shape.
My assumption would be that there was an obvious DAG you could map onto the physical network, and you would just distribute policy. I think it maybe translates into why not use multicast.
Okay. Why not use multicast? Multicast is an approach that I need to learn more about. Part of the reason why multicast isn't attractive from at least my perspective as a developer is that it's really nice to be able to build a system where you don't have to even care what the structure of the physical network is. If you look at the 3 network virtualization systems that I've been intimately involved in, NSX, NVP, OVN, none of them care about the physical network at all. They need to know the IP addresses of the hypervisors, and we did that for a pretty solid reason that our customers didn't they didn't want to have to architect or re-architect their data centers so that they could add support for things like multicast. We looked into it for NVP in particular, but our customers just didn't want to deal with that. They didn't have multicast set up, and they saw it as something that was sort of risky to try to configure.
Well, yeah, I mean, I think it's a cyclic reasoning a little bit here, because the
Yeah.
second you assume the only way you can implement an SDN centralized control at the virtual layer is to assume that you have already have all the distributed control underneath it, then it maybe a little bit defeated the purpose.
Yeah, it would be great to build a system, especially a research system, where you assume you've got a solid multicast setup, and then say, yeah, how do we, what new things can we do given that assumption?
Yeah. All right, so I have another line of questions, which is you had n squared, n number of VMs, n number of servers,
Yeah.
and you're distributing policy. Now, I don't know that you could add another dimension on the richness of the policy, but I can imagine that at least being a constant that starts to grow. Have you thought about or encountered? I would anticipate the more this becomes entrenched, the more people will say, hey, you know, this could be a policy. And suddenly you start piggybacking a whole bunch of stuff on those policies. Have you encountered that? Do you have any thoughts on it?
Well, it does remind me of at Nicira, we initially formed a contract with a very large company, and they were basically what I think of as the worst case. If I remember right, they said they had 10 million ACLs, and that is probably the worst policy that you'll come up with. I think though that I definitely think that the policies get more complicated over time. If you look at partly, I think network virtualization helps with that at least a little bit, because it means that you can create as many network segments, as many logical switches as you want. I think some of the complexity of physical networks comes from the fact that you have a limited number of wires, you have a limited number of VLANs. You have to be restricted by the physical topology of the system. When you can make up as many of these logical switches, et cetera, as you want, I think that makes things a little freer. I have to admit, I don't have a perfect answer here, because I've spent far more time on the low level infrastructure, and I guess maybe to some extent the theory of these things, rather than I haven't spent a lot of time working with particular customers with their system as it grows. But I bet you're right; they get more complicated over
Yeah,
time.
I think it's just an interesting phenomenon that SDN arguably rationalizes and simplifies the configuration policy interface, and suddenly it becomes easy to start dumping everything into policies that get pushed out.
Well,
Brings,
I think that's a tendency that happens in so many areas. When you make it easy to do something, people will do it a lot.
Well, so that kind of brings me again, just to your experience, to a related question, which is the frequency with which these policies change. The starting assumption might be it's relatively early configuration time properties that get distributed and they aren't changing. But again, once you make it easy to do that, it suddenly becomes a frequent event.
When there's an API there that makes it easy, people will change it more. But the sorts of changes that you tend to see percolating through these systems at high rates, I think that tends to be more along the lines of a VM got powered on, a VM got powered off, a VM got migrated. I think there's less of wholesale policy changes than these more frequent events of things starting and stopping and moving around.
Yep. Let me just take a look at the questions there. So there, this is for others to see. There's some links that someone has posted about DDlog. That's great. So we'll have some follow up on that. You might have gotten cut short a little there. If you wanted to say more about that now, then we have a few minutes.
Well, I've been involved in the DDlog project at VMware for a while. It's this, in my opinion, really exciting language because you specify your computation as a program in a data log-like language, where you just specify the computation, and then the compiler automatically makes that incremental, so that when you feed in new tuples, new rows, etc., or you delete them, then it just percolates through and it tells you the changes on the other end. I'm it took me a little while to catch on to how to write data log, but with a little practice, it's pretty natural.
Yeah, I'm a huge fan of specifying the behavior you want that way. Yeah, that's great to see. I'll have to go look at it. So while I have you, I wanted to maybe a little bit beyond specifically what you talked about, but just your experience with OVS. And I know you have another spot you're going to talk about a little bit, but I'm kind of curious about the OpenFlow to P4 transition, and if that has changed, how that's impacted kind of at a meta level you're thinking about OVS, if at all.
OVS, it was originally we meant it as something that would be useful across all sizes of switches, all locations. We hope that everybody would adopt it, but it seems to have really done well in I guess what is arguably the most obvious niche of software and software packet processors, software switches, and more and more SmartNICs. The nice thing about P4 that I'm starting to realize is that it's much more structured than OpenFlow. OpenFlow, at least when you're doing it in software, is almost a free-for-all. You can put anything anywhere, which is really flexible, but as a programmer, it makes it a little harder to figure out how to structure things because you have so many options. When we've been building things in NERPA, in the DDlog based system that's elsewhere here, it's actually helped to form a more solid architecture in advance, because you kind of have to plan the structure of your tables and what you want out of the system. It's arguably produces a better structured, easier to understand system.
Yeah, forces more disciplined thinking on what you're doing. Well, it looks like we're pretty much now at the end of the time slot. So I want to thank you again. Great presentation, and cue Gordon to start getting your slides ready.